Masaki Oshikawa here telling us about Bell states as boundary conditions for CFT.
Thank you, Chairman. And I'd like to thank the organizers for organizing this very stimulating workshop and kind invitation. I'm very happy to come back to this Newton Institute and Cambridge, which is of course very, very important place for science and also beautiful city with my own bicycle. So yeah, my title is Bell states as boundary conditions for safety. So yeah, and my talk is based on collaborations with these two people, and actually I will talk about two works, maybe different problems, but in similar spirit. So both works are done in collaboration with Hoshino-san and Ashida-san. So Ashida-san is a young faculty at University of Tokyo, and actually he's just a second year grad student, but very, very smart. Yeah, especially the second part, I contributed almost nothing, but still this work somehow uses my some old works, so, and also they are related. So I would like to talk about these two works. And so first, so my title says Bell states. Maybe many of you are familiar, but maybe not everybody. So let me just explain what Bell states are. So this is just a maximally entangled state of two qubits. So each qubit has two independent states, 0 and 1. And if you have qubit A and B, you can write down maximally entangled states. So there are four mutually orthogonal ones. So these are called Bell states. And in particular, this one, so in condensed matter, we often use spins. So 0 is spin up and 1 is spin down, for example. Actually, not this one, this one, sorry. So this is like a up, down, minus, down, up. So in condensed matter physics, this is a singlet state for two spin one halves. But and this is known to be a prototypical maximally entangled state of two spin one halves. But these are also entangled in a, okay, so for example, entanglement entropy of these four states are the same. So these are the Bell states, and they play very important roles in quantum information and quantum computation. So I will discuss two different subjects somehow related to this Bell states. Okay, so the first part of my talk is about this one. So this is basically measurement-induced entanglement between two critical spin chains. But the title says entanglement swapping. Again, so actually I didn't know about this entanglement swapping until I was involved in this collaboration. So maybe I will first explain what is entanglement swapping. So, so I took this figure from some relatively recent paper. But the idea is very simple. So there are four qubits. So one qubit here, and another qubit here, and one qubit here, and another qubit here. And in the initial state, these two qubits are maximally entangled. So they are in the Bell state, let's say. And these qubits were also in maximally entangled state. But we can imagine this qubit and this qubit are very far away, let's say, in the space. And you have these two qubits initially uncorrelated, unentangled in your lab or something like that. And then you perform a measurement on these two qubits. And you can imagine performing so-called Bell measurement, that is projective measurement to one of those four Bell states. So I don't know how you can implement this, but you know, in quantum mechanics, in principle, you can write down any Hermitian operator as observable, and then perform projective measurement on the eigenstate of those operators. So you can consider projection operator to those 4 Bell states. And if you perform Bell measurement, projective measurement, the outcome is one of those 4 Bell states. Of course, which Bell state you obtain is determined probabilistically, so you don't know for sure which Bell state you obtain. But anyway, if you perform Bell pair measurement, the outcome is one of the 4 Bell states, which is maximally entangled. So now, after the measurement, these 2 qubits are maximally entangled. Then the question is, what happened to these guys? Because this qubit was initially entangled with this one, and this qubit was initially maximally entangled with this one. And now, so in the initial state, there was no entanglement between these 2, but after the projective measurement, Bell pair measurement, these 2 are now maximally entangled. And actually, this is just a 4 qubit problem, so you can write down the, the actual quantum state, and you can apply a projection operator and so on. And the result is rather simple and interesting. So if you perform this projective measurement, after the measurement, these 2 are maximally entangled, even though you didn't touch these 2 qubits at all, because they are in space, let's say, very, very far away. So this is, so this phenomena is called entanglement swapping, because, okay, so initially you had the entanglement between these two, but after the measurement, you have entanglement between these 2 and these 2. So this is a original simplest version of entanglement swapping. So the problem we considered was kind of a many-body version of entanglement swapping. That is, we start from 2 critical spin chains. So let's say spin 1/2 XXT chain. And of course, initially each chain was in the ground state. So there was no entanglement or correlation or anything between these 2 chains. But then you separate each chain to 2 regions. And on left-hand side, for example, you pick 1 spin from chain 1 and 1 spin from chain 2, and perform Bell pair measurement between these 2. And likewise, you pick this spin and that spins and perform Bell measurement on these 2, and so on, so on. So you perform Bell pair measurement on pair of spins in this region. Then after the measurement, you project quantum state to one of the Bell states. So this spin and this spin are maximally entangled. This spin and this spin are maximally entangled, and so on, so on. But you didn't touch these spins and these spins. But the interesting point is that, like in the simple 4-qubit version of entanglement swapping, because initially there was some entanglement between this region and this region, and this region and this region. After Bell pair measurement, you kind of enforce entanglement between this part and this part. Then after the measurement, even though I didn't do anything on these spins, the entanglement is somehow generated between this region and this region. So this is a many-body version of entanglement swapping, or we can call measurement-induced entanglement. And the question we wanted to answer was how much entanglement do we have between this region and this region after this measurement? And okay, so we can consider this for many different systems, but we considered one of the simplest and the most fundamental model for quantum magnetism or quantum many-body problem, that is spin 1/2 XXT chain. The Hamiltonian is given like this, and there is an anisotropy parameter, and for delta between -1 and 1, this is gapless. The low energy physics is described by conformal field theory, actually, which is this free boson field theory. And in condensed matter physics context, this free boson effective field theory is called Tomonaga-Rattinger repeat. And each spin operator has this effective expression in terms of this boson field. So in the initial state, each chain was in the ground state. So each chain is described by this Tomonaga-Rattinger repeat or free boson. So theoretically, we need to consider two-component free boson field theory. Component 1 describes chain 1, and component 2 describes chain 2. And then now I do Bell pair measurement on one region of this system of two spin chains. So the four Bell states can be written like this, parameterized by B1 and B2. So B1 and B2 are 0 and 1. And so there are four Bell pair states labeled by 00, 01, 10, 11. And for example, Bell pair 00 state is, so you put B1 equals 0, and this B1 bar is a conjugate of B1. So if B1 is 0, B1 bar is 1. So you have 1, 1. The minus 1 to power of B2 becomes 1. By the way, this light is intended or?
What do people prefer? Do people prefer the light on or?
Yeah, some, but I think it's
Too much? Too much? Sorry.
yeah, maybe you can go.
Yeah, thank you. So yeah. So for example, let's consider this Bell state 00, which is up, up, plus down, down. And you do Bell pair measurement on one pair of spins. And let's suppose that you obtain this 00 state. Then this state is up, up, plus down, down. Means that the direction of spin in two chains must be parallel, pointing the same direction. So on the other hand, I had this bosonized expression of sigma z, and there are two terms, but this second term, staggered term is more dominant, more important in field theory, so we focus on this. So basically this sigma z is given by cosine of 2 phi. But now if I get this Bell pair 00 state, then this cosine 2 phi must be the same between two chains, which means that locally we impose this phi 1 equals to phi 2 condition when we get this 00 state. And likewise, it's a bit more complicated, but there is a dual field theta to phi. And this sigma x and sigma y is described by basically by cosine and sine theta. And in quantum mechanics, we learned that this up up plus down down is one of the total triplet state. So this actually gives total spin x equals to +1 between these two spin 1 halves. So that means that you maximize this sigma x in some sense. So by this physical consideration, this Bell pair state also corresponds to imposing this theta 1 plus theta 2 equals to 0 boundary condition. So this Bell state can be de-interpreted in terms of field theory as this kind of boundary condition. Then, okay, so the real problem is more complicated because every time you measure, you don't know which Bell state you obtain. So it's actually, there is some correlation between neighboring measurements, so it's not completely random, but basically every time you measure, every time you do pair measurement, you get randomly one of the 4 Bell states. So the general outcome is very complicated, and the analysis is more complicated. But to simplify the problem, we focus first on a special case, that is a uniform outcome case, or we can say this is a forced measurement. That is, you do a Bell pair measurement, and every time you expect or you enforce the outcome to Bell pair 0, 0. That means that if you obtain different outcome, you throw out the result. That is okay, not very efficient, very inefficient, but in principle you can do that. But anyway, if you do this, then in a region of the system, you have Bell state 0, 0 for all the pair of spins in this green region. And in this unmeasured region, the quantum state is not touched. But as I mentioned, you induced certain entanglement between 2 chains by doing this measurement. And what we want to do is to calculate the entanglement entropy between 2 chains in this state after doing this Bell pair measurement, especially this forced measurement to uniform outcome, every pair being in Bell state 0, 0. And the standard way to compute the entanglement entropy is to use a replica trick. So first, we consider n copies of the same system, and then consider taking a partial trace and take the nth power of the reduced density matrix, and then take the trace, which corresponds to replica partition function. And you can formulate this in field theory because the initial state was the ground state of certain conformal field theory. So we can imagine starting from any generic initial condition and do the imaginary time evolution for infinitely long time, and then you obtain a ground state at this section at tau equals 0. Then you enforce the boundary condition I mentioned corresponding to the Bell state on this green region, and the purple region remains a kind of free boundary condition. But then you try to take a partial trace and take the nth power of the density matrix. Then consider the replica partition function. So now the problem of computing the entanglement entropy is reduced to a calculation of the certain partition function with some special boundary condition on the cross section of this infinitely long half cylinder. But for a while, we didn't know how to calculate this, although the problem is kind of well defined. So eventually we could compute this boundary partition function. But for that, I needed to go back to the more fundamental problem, basic problem. That is just an entanglement entropy in conformal field theory between one finite segment of length L and the rest of the system. So of course this is a super famous problem now, maybe textbook material, and the result is that if you have a conformal field theory in general, and if you have this finite length segment of length L, and if you compute the entanglement entropy between this red region and the rest of the system, blue region, the entanglement entropy is C over 3 times log of this length plus some constant. And this C is the central charge of conformal field theory. And this was initially derived by this Holze, Larsen, Wilczek paper in '94. And later, this was re-derived and extended to many interesting directions by Calabrese and Cardi. So this is, of course, very, very, very famous work. But I have to confess that, of course, I went through, Calabrese, Cardi paper several times, and I was supposed to know, why this is the case, but I didn't really understand this in the sense that often students come to me and ask, Professor, I found this paper, but how can we derive this formula? Then I couldn't go to Blackboard and explain everything. So I was always saying like, well, you can look up Calabrese Cardi paper and they explain everything, something like that. Which means that I didn't really understand why this is the case. So, but to solve our problem, I felt like I needed to understand this better. So I will explain how now I understand this better. Although I'm not claiming any novelty, probably. For some of you, what I'm going to tell you is kind of trivial or everybody already knew or something like that. But anyway. So yeah, before that, this famous formula was derived by this Holze, Larsen, Wilczek paper. And of course, everyone knows Frank Wilczek, Nobel laureate and famous for many, many other works. And I didn't know Larsen very well, but he's high energy theorist. So he was student or something of Wilczek. And he's now a professor at the University of Michigan or something. So typical successful, theoretical physicist, high energy physicist. But what about the first author, whom I didn't know very well? So out of curiosity, I searched for this first author, and I found him on internet. So this is the first author of this famous paper, Christoph Holze. And actually, he is still in academia, and actually he is a director of some institute. But it's not physics institute, it's an institute in Berlin, but the Institute for Cultural Inquiry. And so this is his bio. So he actually studied physics at Oxford, then went to Princeton for PhD. And this famous paper was his PhD thesis under the guidance of Frank Wilczek. But interestingly, after writing this famous paper in physics, he went to Columbia University to study German literature. And he obtained a master's in, I don't know, philosophy or something. And then eventually a PhD in, by a thesis on paradoxical pleasures in aesthetics or something like that, which I don't really understand. So he went back to Germany as a postdoc at Max Planck, but not optics, not complex physics of complex systems, but Max Planck Institute for History of Science. And then, he's now, director of this institute. So he switched the field completely, apparently. But it seems that he's still proud of his work in physics, so this physics as his specialty. Okay, so this nothing to do with my scientific content, but still I found it's very interesting. So very interesting career trajectory. Anyway, so this is how I understand better about this famous result. Is that so by definition, first we consider Renyi entanglement entropy. That is trace of nth power of the reduced density matrix. So you have ground state, projection to the ground state, and then trace out the density matrix in outside region, and then calculate this, and then you can take the limit to obtain the entanglement entropy. So for this, I introduce n replicas of the field, and also because of the density matrix has a ket part and bra part. So for each replica, I have bra and ket. So which means that in total we have 2n replica of the same the field appearing in the conformal field. Then this boundary partition function, which we use to derive the entanglement entropy, is a boundary partition function with 2n replicas, and you, as I said, this cross section corresponding to tau equals 0, and you impose a different boundary condition on this blue side and the red side, because in blue region you first take the partial, you first take trace, which means that you contract ket and bra field, which means that you impose this kind of boundary condition. The bra field in each replica must be the same as the ket field of the same replica. That's the boundary condition you impose in this blue region. And then in this red region, you didn't take the partial trace, but you take the trace only after taking nth power, which means that you have n set of bra and ket field, and by taking this multiplication of the density matrix, means that the ket field of J's replica must be connected to bra field of J plus first replica, and so on. So we impose the different boundary conditions, and we need to compute the partition function for this given imposed boundary condition. But this can be interpreted as a correlation function of the boundary condition changing operator. So you insert boundary condition changing operator here and there, which kind of changes the boundary condition from this one to that one. So you can interpret this as a boundary condition changing operator, correlation function. Then by conformal mapping, so in the original setting, I had the boundary, red boundary here and the blue boundary outside. But you can try conformal mapping to send this point to minus infinity and this point to plus infinity. Then what you get is infinity long strip with boundary condition, blue boundary condition on one side and the red boundary condition on the other side. So then, as I said, the original boundary partition function is related or interpreted as a correlation function of the two boundary condition changing operator. But the behavior of this correlation function is determined by the scaling dimension of the boundary condition changing operator. So we just need to determine the boundary scaling dimension of this boundary condition changing operator, which I denote as delta sigma. But if you look at the boundary CFT textbook or one of Cardy's fundamental papers, you can read off this boundary scaling dimension of this boundary condition changing operator from the difference between the ground state energy. So this is a ground state energy of this system. So you can now consider time evolution as a vertical direction. Then the spectrum is determined by Hamiltonian with boundary condition blue on left and red boundary condition on the right. And this is a ground state energy for this combination of the boundary conditions. And the difference, in the difference, you put the same boundary conditions on the both sides. Then usually this configuration gives you higher ground state energy because the boundary condition is kind of relatively twisted. And this difference actually gives you the scaling dimension of this boundary condition changing operator. So we just need to compare the ground state energy between these two. And so because each of the boundary condition can be summarized in this simple form, actually we can compute the ground state energy of these two situations relatively easily. That is, okay, so we start from this blue-red one. In this case, you pick up, let's say, ket field, which one? Yeah, blur field of replica 1, for example. Then you move to the left, then you hit the blue boundary. Then, according to this boundary condition, phi 1 of blur is smoothly connected to phi 1 of ket. Then you bounce back as phi 1 ket. Then you hit the right boundary. Then you had the phi 1 ket, but that is smoothly connected to phi 2 blur. So you are reflected back as phi 2 blur. And then you hit the left boundary, then phi 2 blur is smoothly connected to phi 2 ket, and so on, so on. So you go back and forth, and starting from any field, you are eventually connected to all the components of the replicas. So at the end of the day, this configuration is identical to periodic boundary condition of the single field. But so periodic boundary condition means that this situation is equivalent to single field defined on the link, but the circumference of the link is 2n times L, because you go back and forth, and eventually you come back to where you started. And for the periodic boundary condition, the ground state energy is given by this famous formula. So this is a conformal anomaly, or the universal Casimir energy. So pi c over 6, c is central charge, but the times 1 over the circumference, but the circumference is now 2n times L. Okay. And by the way, this on the other hand, this difference state has same boundary condition on both sides. In that case, again, you can map this problem to periodic boundary condition, because you start from phi 1 blur, then you hit this left boundary, then phi 1 blur is connected to phi 1 ket, then you bounce back and you hit the right boundary, but the right boundary now has the same boundary condition. So phi 1 ket is bounced back as phi 1 blur. So this is again equivalent to periodic boundary condition, but circumference is just 2L. And also, each replica is, okay, blur and ket are connected, but field with different replica indices are completely decoupled, which means that the ground state for this configuration is pi c over 6 times 1 over 2L. 2L is the circumference, but there are n copies still, so the ground state energy has this factor of n. So you just need to subtract this from this, and then, okay, so this is the result. So the scaling dimension of the boundary condition changing operator is given by this. And if you plug in to this boundary partition function, the boundary condition changing operator correlation function, then you can compute the Renyi entanglement entropy, and taking the limit, you can reproduce the famous formula. Okay, so of course this is completely equivalent to what was already discussed in Jose Larsen-Wilczek paper, Carl Riccardi, but somehow usually those papers are not written in a way I, as a condensed matter physicist, can understand easily. But in this way, now I can go to Blackboard and explain to the student. That's my point. And once okay, so another interesting point is that, so this famous entanglement entropy formula for CFT is somehow related to this another very fundamental result in conformal field theory, originally derived by Brete-Cardy, Nightingale, and Affleck, that is this universal Casimir energy in CFT, or low temperature specific heat at a finite temperature. Okay, so that was just how I finally understood the very old and fundamental result. But once I understood this, I can easily compute the boundary partition function for this one, because this problem can be reduced to the ground state of the periodic boundary condition case in similar way. Of course, different, because result must be different, but this can be computed in very, very similar way. So so again, this is a correlation function of boundary condition changing operator, which can be calculated by the ground state energy difference between imposing two different boundary conditions on each side versus imposing the same boundary condition on both sides. And this can be reduced to the ground state of CFT. And this is ground state energy for this configuration. And for this, I have the same ground state energy as before. And I just need to subtract between these two. Then, now the boundary scaling dimension of boundary condition changing operator for our problem, not the original set up by Jose Larsen Wilczek. But logic is very, very similar, and by similar calculation we can obtain this. And using this, we can compute the entanglement entropy after doing bell pair measurement in our setup. So, and finally, we can take the replica number n goes to 1 limit, then we can obtain the von Neumann entanglement entropy. And by simple calculation, this is given by 1/6 times log of the arc length of the subsystem. So this has very similar structure to the famous Jose Larsen Wilczek entanglement entropy CFT, but coefficient is different. So the famous result was C over 3 times log, and in our problem C equals 1. But this after this bell pair measurement, the entanglement entropy we found was 1/6. So it's exactly half of the original Jose Larsen Wilczek entropy of CFT, which there may be deeper meaning why this is exactly half, but I don't know yet. But I think in general, we cannot exceed the original entanglement entropy. So in general, we expect some reduction. So in fact, we found some reduced entanglement entropy, which is probably consistent with general principle. But at least we did find how much the entanglement is actually reduced compared to the initial state. Okay, and then Hoshino-san did a numerical calculation to obtain the entanglement entropy for between two chains for our setup, and he did find 0.165 to 0.168. And which is in good agreement with theoretical prediction 1.6. And another interesting point is that so this is universal for conformal field theory of free bosons, Tomonaga-Rattinger. So this does not depend on the so-called Rattinger parameter or compactification radius of free boson. So in terms of lattice model, this result does not depend on the anisotropy parameter of the XXZ chain. So this is a theoretical prediction, which is in agreement, at least roughly, with numerical result. And also, if you are interested in linear entropy, this n-dependence also matches theoretical prediction. Okay, but what we discussed so far was in a very
Can you explain the log sign?
Huh?
Log sign. You have a log sign.
Mm-hmm.
That's the different from Wilczek.
Oh, sorry, I skipped the explanation, but log L is entanglement entropy of finite segment in infinite chain. But if you consider CFT on a finite ring,
Is a finite temperature result?
well, finite length result in this context. But of course, in some context, you do this conformal mapping to obtain a finite yeah, similar idea. Sorry, yeah, this finite length result is more useful to be compared to numerical result because of course the numerical calculation is usually done in finite size. Okay, so but I have to say that our CFT calculation was done for very special case of so-called forced measurement. That is, every time you do Bell measurement, Bell pair measurement, the outcome was assumed to be the same, 0, state, which can happen, but only with very, very low probability. So probably more interesting is you do Bell pair measurement, and every time you get some different Bell state, but still you can compute entanglement entropy, and you can consider average over all the measurement outcome, which is probably more physical. And we didn't know how to compute this with conformal field theory, but numerically he could do the simulation. And interestingly, the result was almost the same as uniform forced outcome case. Okay, so in the end, this coefficient was 0.17 times log. So this 0.17 is pretty close to 1.6. And we didn't know why this is the case, but after our paper, there was a paper by Romain Vasseur and his collaborator, and they improved, extended our argument. So now probably they have some explanation about this, but I haven't gone through this paper, so I cannot explain what they did, but if you are interested in this program, yeah, they have better understanding, I think. So to summarize the first part, we consider the measurement-induced entanglement or many-body version of entanglement swapping between two spin-1/2 XSG chains, which can be described by Tomonaga-Rattin-Jarikit or free boson conformal field theory. And yeah, we could, at least in a special case of forced measurement, we could compute the universal behavior of the entanglement entropy. So this post-measurement entanglement entropy using the boundary CFT by using a replica trick and identifying this boundary partition function as a correlation function of boundary condition changing operators. And the technique is kind of straightforward generalization of the celebrated CFT result. So somehow, even for this kind of new physics problem, inspired by quantum information ideas, boundary conformal field theory apparently works very well. So yeah, this kind of approach will have many more generalizations, I think. So yeah, for the remaining time, I want to also briefly discuss this paper, this work, which discusses rather different problems, but technically this can be also discussed in a similar way. So again, I'm not expert on quantum information, so I learned about this very recently, and still I don't understand this stuff very well, but anyway, to motivate why we consider this problem, I will try to explain the background. So first, we have a collection of qubits. So each qubit has 0 and 1 and the superposition of 0 and 1. And then we can consider Pauli operators, x, y, and z. In condensed matter physics, we often use sigma 1, 2, 3, but they are in quantum information literature, they use x, y, z, but they are the same thing. So for example, x is Pauli x or Pauli 1, which is this matrix acting on single qubit. And we can also introduce sigma 0, which is identity operator, 2 by 2 identity operator. Then if you have several qubits, we can consider tensor product of these Pauli operators. So in general, we can consider this kind of operators, which we call Pauli strings. So at each site, you choose one of these four operators, identity or X, Y, or Z. And you choose one of those four operators at each site. Then as a whole, this defines certain operator acting on the Hilbert space of n qubits, and this is called Pauli strings. And if you take the product of two Pauli string operators, again you have Pauli strings, because for example, x times y is iz. But you may get some coefficient. So Pauli string operators with coefficient plus minus 1 and plus minus I form a group, which is called Pauli group. And then in quantum computation literature, there is an important concept called Clifford gates. So Clifford gates are quantum gates, or some operations on qubit Hilbert space, which can be constructed by or generated by these three fundamental types of quantum gates. So first one is called Hadamard gate, which is just expressed as this simple matrix on 2 by 2 matrix acting on single qubit. And another is this S gate, which is diagonal in this space is but 100I. So if you take square of this one, you get a Pauli Z. So this is like a square root of Pauli Z. So these are just two single qubit gates. So you cannot do much, but there is one very important gate acting on two qubits, which is control knot. So that means if first qubit is in 0 state, you do nothing, identity on second qubit. But if first qubit is 1, you flip the second qubit. So this is called C-knot gate, which can be expressed as this 4 by 4 matrix or operator. And you can build more complicated gates combining many of these things, which are called Clifford gates. But Clifford gate maps element of Pauli group to another element of Pauli group, which you can see easily from these definitions. So it turns out that if you only have Clifford gates, then you cannot do much as a quantum computation. So to understand this, there is another important concept, stabilizer state. So that is, so we have this Pauli group consisting of Pauli strings times some coefficient. But there can be some subgroup of this Pauli group, which is abelian, commutative. Then if you take this abelian subgroup, stabilizer group, there can be eigenstates of any element of this stabilizer group with eigenvalue plus 1. For example, if you consider this trivial state, just a tensor product of 0 qubit state at each site, then this is actually stabilized state for stabilizer group generated by these Z operators at each site. Because for each Z, if you act, you get just an eigenvalue plus 1. So even for products of these Z's, you always get eigenvalue plus 1. So this is kind of trivial example of stabilizer state with respect to this very simple stabilizer group. But point is that so if you have Clifford gate, even though this Clifford gate consists of many other S or control knot, and it might look very complicated, you can see that the Clifford gate maps a stabilizer group to another stabilizer group, which might look more complicated than this one. But still, stabilizer group is mapped to stabilizer group, which means that if you map this 0 state by the same Clifford gate, then the states you get might look very complicated, but are still stabilized. And that has some important implication in quantum computation, because there is a Gottesman-Knew theorem which says that, okay, so let's consider some class of quantum computation which can be done with some initial state, which is very simple zero state, and you just use only Clifford gate. And you are allowed to do measurement only in Pauli basis. So if your quantum computer is restricted to these conditions, then this theorem says that this entire thing can be efficiently simulated by classical computers, which means that even if you use very, very complicated set of Clifford gates, you don't get the quantum advantage compared to classical computers. So of course, people are working on quantum computers because we believe that it can go beyond any classical computers. So this means that you need to go beyond at least one of those conditions in order to get the quantum advantage. Then there's an interesting result. I forgot who, Kitaev and somebody. So it was found out that even only with Clifford gates and a measurement in Pauli basis, if you can provide some quantum state which is not a stabilizer state, then you can combine this quantum state with Clifford gates to implement non-Clifford gate. Then you can achieve so-called universal set of quantum gates, which can realize, in principle, any quantum computation, which can have quantum advantage. So that means that even your hardware is somehow restricted to these conditions. If you can somehow supply a quantum state which is not stabilizer state, then you can get a quantum advantage. So somehow these non-stabilizer states are called magic states because you initially had some classical equivalent computers, but by supplying this magic state, you can have quantum speed up. So this magic state is of strong interest in this quantum computing community. So then what we want is a quantitative measure of magic or non-stabilizerness of given state. Because let's say you give me some quantum state and I want to use this quantum state as a resource for quantum computation. But then if the state you give me was just a stabilizer state, then there is not much advantage. But if you give me some quantum state which is not stabilizer state, then it is useful. So we want to quantify how far is the given state is from stabilizer state. So we need a measure of non-stabilizerness. So there are several proposed measures, but one practically useful thing, which is easier to evaluate, is this stabilizer linear entropy. That is kind of entropy, linear entropy, defined by a probability distribution, fictitious probability distribution, which is defined by the expectation value of all the Pauli strings. So we consider all the possible Pauli strings and consider expectation value with respect to the given quantum state. Then taking square, it defines certain probability distribution fictitiously, then you can define the entropy as usual. So this is a stabilizer linear entropy. And you can easily see that if your state is a stabilizer state, then this is zero, and vice versa. So this can be useful as a measure of the non-stabilizerness. So we want to compute this stuff. So I'm running out of time. But, so we just want to evaluate this. But the trick, which it was not me who found this, my collaborators. But there's a trick to identify this expectation value as an inner product between states in doubled Hilbert space. So, for example, yeah, actually, so we had 4 Pauli operators, identity XYZ at each site, and expectation value of each such Pauli operators can be somehow mapped to amplitude or inner product between a doubled given space, given quantum state and Bell state. So this is a point. So far, Bell state didn't appear explicitly in our discussion, but now we can replace this expectation value by inner product with Bell state. So then we can apply similar conformal field theory technique. So yeah, I skip the details, but yeah. So again, we consider path integral formulation, and yeah. So cut at tau equals 0 corresponds to ground state. Then we want to evaluate the expectation value of all the Pauli strings, but this can be replaced by some exponential of ZZZZ and XXXX between neighboring replicas. So this is like a boundary interaction or interaction term only present on this cross section. So this is like a defect line. So in particular, we consider the critical Ising chain as a target. So that is a physical question is I have a critical Ising chain and I have a critical ground state. Then we want to measure how far is the critical Ising ground state is from stabilizer state. That is, what is the non-stabilizerness of the ground state of the critical Ising model? That's a question. And by mapping the problem to conformal field theory, we can we can map this problem to replicated Ising CFTs with some defect line introduced, and we just need to calculate the partition function in the presence of defect. Okay. And we need 2 alpha replicas of Ising model to calculate the SRE with the linear index alpha, but 2 replicas of the critical Ising model is mapped to so-called Z2 overfold of the free boson CFT. So this is very, very old result in CFT. So each pair of Ising can be described by this kind of field theory. And at the defect line, we introduced a defect interaction like this to mimic stabilizer linear entropy. And the ZZZZ term is given by this cosine of phi I minus phi I plus 1. And the XXXX term is mapped to this kinetic kind of term. But, this is marginal. Or, so maybe at the defect line, this is even irrelevant, but this is RG relevant, having a scaling dimension 1/2. So from field theory viewpoint, this is more important because this is RG relevant. So we only consider this term. Then what happens is that, so we have defect, but we apply folding trick. Then we can formulate the problem as a boundary of 2 alpha replicas of Z2 overfold theory. And at the boundary, we have this kind of interaction. And this is relevant perturbation. So this will drive the boundary condition to different one. And this tend to pin this difference to 0, which means that in terms of this boson field, eventually the boundary condition should look like this. That is, all the difference field is pinned to 0. So Dirichlet boundary condition. But the center of mass field is not affected by this. So this center of mass remains free or noise. And but this is not just free boson, but Z2 overfold. You need to identify phi is minus phi. So you need to construct the overfold version of this thing. And in this way, this stabilizer linear entropy, the measure of the non-stabilizerness of given quantum state, is mapped to the boundary free energy. So in fact, this stabilizer linear entropy, we generally find that there is a non-universal term, which is proportional to the length, but the second constant term is universal, because this is in fact related to the universal Ludwig-Affleck. Okay, so log G should be boundary entropy. So there's Affleck-Ludwig here, bound so-called ground state degeneracy of the boundary. Anyway, so this is very well known quantity, and we can compute this boundary entropy for this particular boundary state we studied. So this is a result for the universal constant term, which can be compared with numerics. So this horizontal axis is a Renyi index, and this vertical axis is this constant term in the stabilizer Renyi entropy. So yeah, I don't know how much practically useful this result is, because a large part of this SRE, measure of the non-stabilizerness, is contained in this non-universal term. It is only this relatively small constant which we can predict from field theory, but still, at least academically, it is kind of interesting. Okay, yeah. So yeah, again, CFT works, and I hope this is one of the many phases of boundaries and defects. Thank you.
Maybe I missed one point. How do you define polystring in CFT? How do you define polystring?
Oh yeah, so polystring is an operator, acting on qubit. So the correspondence is of course not so simple. So in this case, yeah, so what we used was, sorry, yeah, I skipped, but so two pair of two Ising model can be described by this Z2 overflow or free boson. But then it's also known that this ZZ operator can be described by this cosine phi of this phi field. So this is known result for pair of Ising models.
Is map a very precise map?
Well, this is supposed to be exact in the low energy limit. So this is an effective low energy field theory. So of course, this kind of field theory cannot describe entire thing, but this kind of field theory is believed to describe the low energy limit or long distance limit. So that part, we believe this operator, for example, if you want to calculate a correlation function between this ZZ and ZZ, then you can compute correlation function between this cosine phi and cosine phi in field theory. And in the long distance limit, they agree exactly that. Yeah.
So by your numerical calculation, you finally show some plot.
Mm-hmm.
You use this dx operator to compute.
Well, okay, so I didn't explain, but this numerical result is independent of field theory. So this was calculated directly on this
yes, so
spin
my question
chain.
is, for that result, do you use this dx operator? The only
Well, yeah. At least okay. So I forgot how my collaborator actually did this numerical calculation, but the numerical calculation is done in faithfully to the original definition, which is the expectation value of Pauli string. Yeah, maybe he didn't actually calculate the expectation value of Pauli string, but maybe he mapped this to some other quantity, but it's supposed to be exactly the same.
Okay, thank you.
I was wondering about this factor 1/2 in the first part of the law.
Mm-hmm.
Can you trace what happens to the entanglement entropy, this sort of step by step when you do these projections, this entanglement swap?
Step by step, which means at every measurement or something like that.
Yeah, like at each measurement, can you see like you're swapping like 2 entanglements for 1 entanglement or something like this?
Yeah, I don't know. Okay, so I don't think we have any calculations which can answer your question, but maybe I repeat what is the point is that, okay, so before doing this measurement, each chain was in the ground state. So each chain was described by conformality theory. Then this part was entangled with the remaining part of the same chain. And this entanglement was 1/3 times log L, as in the famous result. And likewise, this part A prime was entangled with the rest of the system of the same chain. And this entanglement was 1/3 times log blah, blah, blah. But after this Bell pair measurement, so these spins are now maximally entangled. But this guy, can no longer entangle with these guys. So instead, these guys are now entangled with this A prime. And this entanglement is now 1/6. That's our result. So which means that these guys were originally entangled with these guys with 1/3 times log. But after this measurement, these guys are now entangled with these guys, but only with 1/6 log L of entanglement entropy. And yeah, as I said, I don't know exactly why. So as you said, you suggested maybe it's interesting to consider gradually increasing the number of Bell pair measurement, but we don't know. We don't have any concrete result right now. But maybe we can investigate more. Yeah, this is maybe physically most interesting part.
Maybe I can give a comment. So it might be related to there are 4 Bell pairs. So it's like a symmetry resolved. You have to project to one. It's not the full von Neumann entropy, but some resolved von Neumann entropy. The factor 2 may come from this result.
Yeah, so what I was told by some quantum information guy was that so in this simplest setting, this was maximally entangled and this was maximally entangled, and after Bell pair measurement, these are maximally entangled, and then these guys are also maximally entangled. But in our problem, originally this entanglement was far from maximal. This was much less than maximal. And in that case, I think the general principle is that after the measurement, this entanglement can be smaller than this one. And in our case, we somehow found this is 1/2 of original entanglement. I don't know why exactly 1/2. But what quantum information guy told me was that for not maximally entangled case, in order to maximize the post-measurement entanglement, maybe there is different optimal way of measuring these pairs or something like that.
Or maybe I can comment on this. This is actually a measure, and this is called the entanglement of assistance. I have like a tripartite state, and the question is how do we have to measure the third state such that A and B have the maximum amount of entanglement. It's called the entanglement of assistance, and it's a very difficult problem to actually find this optimal thing. But of course, in this setting, it's very easy. But that's actually a question. So why did you stick to the Bell states? Because there's infinitely, this entanglement swapping works with any maximally entangled state, not just the Bell states. So have you checked whether you get the same results by doing other measurements in different maximally entangled states?
Yeah, good question. Yeah, short answer is no.
So what is special to this basis for you?
Well, at least we could find this simple boundary condition which corresponds to imposing this. Yeah. So for more general maximally entangled state, once we found boundary condition description of your state, then we can probably do the similar trick. But at least for this, boundary condition happens to be simple, so this is easier for us to deal with. But,
For the other states that Frank's asking about, you expect more general boundary conditions or something?
I don't know. I have to do the calculation. But in any case, in field theory language, even if you start from different boundary conditions, somewhat different operator, we expect certain degree of universality. That is, you start from different boundary conditions, but eventually the IR limit can be same. So probably that's going to happen. And for any maximally entangled pair, probably the final result is probably the same. That's my guess. But we have to do the calculation to be the issue.
I'll ask about the second part, just to understand the motivation. So are you proposing to use like the critical easing model as like a resource state for?
Well, yeah, in principle, yeah. Although, yeah, okay, so I'm not totally sure if this is really practically
I
useful
remember
in
that
any way.
Zhenghan Wang at KITP, he was making this point one should use gapless models.
Mm-hmm.
Yeah,
I guess the question probably is so we from quantum computation perspective, we want non-stabilizer state as quantum resource. So the bigger the SRE is, it's more resourceful. But then how to prepare such state? So if the ground state of this kind of Ising type natural model in condensed matter, AMO physics, maybe easier to realize, I don't know. So in that case, maybe we can consider using this kind of state as a resource. And it has certain SRE means that it can work as a resource. But as I mentioned, large part of this resourcefulness is related to non-universal quantity. So I'm not sure if this kind of field theory analysis can be practically useful for this point. But at least now we know that there's a non-universal part proportional to the system size, plus small constant which is universal, which may be showing the limit of field theory. What field theory can tell us about this resourcefulness, maybe this shows the limitation of this approach in some sense.
So maybe we'll continue then with this discussion at lunch. So let's thank Masaki again.